Hello friends, this is the assignment solution of vibration. I gave you some 5 questions in last time, but no one responded for these questions. So let me solve those questions. The first one is 10 kilogram fan is fixed at a lightweight beam. The static deflection or the static weight of the fan deflects the beam by 20 millimeters. If the blade is designed to spin at omega is equal to 15 rad per second, and the blade is mounted off center, which is equivalent to 1.5 kg mass at 50 millimeter eccentricity from the axis of rotation, and determine the steady state amplitude of vibration. So this question asks us to find the steady state amplitude x. So what it says, we have a fan here. This rotating fan is omega. Omega is 15 rad per second is given, and it is rest on the lightweight beam, elastic beam. So this beam is deflect when the weight of this thing pushes it. So the deflection, static deflection, due to the mass of this combined system is 20 millimeter. So that means this system deflects like this. So let's go to solution, how we can solve it. So what we can see is delta is equal to 20 millimeter is a static deflection. This is due to the mass which experienced on the elastic beam. So this elastic beam, we consider it as a spring system. So let me take some pen, pointer or pen. So this beam is considered as elastic beam, so that it will deflect. So that what the this deflection relate kx is equals to mg, that is from static condition. So from this we can calculate. Actually, we have given mass is given. X is the static deflection delta. So K delta is equals to mg. K delta is equal to mg. So from this we can find the stiffness of this elastic beam. So we can consider it as elastic. And when we consider it as elastic, we are talking about the spring. So the spring constant, equivalent spring constant of the beam is equals to Q is equals to mg over delta. So mg is equals to which is equals to 10 times 9.81 over deflection 20 millimeter means 20 times 10 to the power of -3. We have to use metric system times 10 to the power of -3, which gives us the stiffness of the beam, which is equals to 49.05. 49.05 Newton per meter. Okay, Newton per meter is the stiffness of the elastic or spring thing. Once we get this K, we can find the natural frequency of the this elastic beam. Okay, what is the natural frequency? Okay, natural frequency omega n is equals to radical of K over m. Okay, so K is already calculated. This value 4905. 4905, and m is 10. So from this we can get the natural frequency of the beam as 22.15. 22.15, which is in rad per second. Per second. So we can compare here. The forcing frequency is 50 rad per second. Natural frequency is 22.15. So the resonance problem is there is no condition of resonance in this value. So it is far away from omega. Omega n and omega are different. So we don't hesitate about the resonance situation. So how we can find the what we call this steady state amplitude of vibration? Let's go for, so we have rotating blades. So these three blades are rotating about its axis. Okay, this is the axis of rotation. Let's consider this as axis of rotation. Okay. So on this axis of rotation, it is rotating like this with 15 rad per second. 15 rad per second. Now let's coincide this one of the blade to the vertical axis in the y. Sorry. So when we there is an eccentric mass which is in distance 50 from the center, from here to here, 50 millimeter. And this eccentric mass, a small eccentric mass, is considered as 1.5 kg. 1.5 kg. Okay. So this small mass is in 1.5 kg, and which is away 50 millimeter away from the center of rotation. So during this time, what we can do, the forcing frequency comes from this mass. Okay, F naught. The forcing frequency F naught is here. So this F naught is equals to this small mass m times acceleration in this direction. Acceleration. And acceleration in this direction is equal to omega square r. Omega square r is the radial acceleration of this mass. Okay, so this F naught is equals to m times omega square r. So that gives us 1.5 is the mass times omega is 50 squares, and R is 50 times 10 to the power of minus 3, because this is millimeter. Okay, 15 times 1.5. This is not 1.5, but 55 of 50 times 10 to the power of minus 3. So this forcing, the continuously forcing, the force amplitude is 16.8 16.875 meter. Okay, so this is F naught. When we are calculating this F naught, to find the steady state amplitude, we have this relation. X, steady state amplitude X is equals to F naught over K, F naught over K over 1 minus omega over omega n, the whole square. Okay, so on that, F naught is this amount, that is 16.875, and K is actually this F naught over K is by itself delta. We can replace that one. Anyways, let's go using the numerical value already available. So that is 49. K is 49.05. And another 1 minus omega is 15 over 22.15. This is as a whole square, which gives us 0.00635 meters. 635 meter, or which is equals to 6.35 millimeter. This is the steady state amplitude of vibration. Okay, so that is for the question number 1 here. And another question is, you are designing a stylish fan that uses only one blade. Approximate that the blade has a narrow plate with a density per unit length 20 grams per centimeter. The base weight of the rest of the device, except for the blade, is 4 kg, and the whole thing is mounted on a lightweight beam. If the spring constant of the beam K is equal to 1000 Newton per meter, find the length of blade. Then, while causing a resonance, this is at a resonance, it is operating at a resonance condition, that is 50 rad per second. So the natural frequency of vibration also considered 50, near to 50 rad per second. So that how we can design that? Let's see. So this is the blade, only one blade. So we have given total mass 4 kg. Stiffness of this this also elastic, means we can consider it as a spring material. Okay. The beam is considered as spring beam. So the rotational speed is forcing frequency 50 rad per second. Density is 20 grams per centimeter. What we are going to find is the length of this blade. Let's consider this as a length of the blade, L. So how we can calculate this thing? So in order to calculate this, we have this relation: total mass M total is equals to bigger mass, means mass of the whole system, plus the mass of the blade itself. Okay, so total mass is 4 kg. This complete assembly of the system is 4 kg. Okay, just 4 kg. Now the blade mass is also there, so N we can say. Another, this M is calculated from the given property. There is this density per unit length of this thing is given. So how we can find M is equals to rho times L. Rho times L. But the density is given in gram per centimeter, so we have to change it to kilogram per centimeter. So that means 1 gram is equal, means 1 kilogram is equals to 1,000 grams. So, and the centimeter is equals to, when we convert it to meter, it is 10 to the power of -2 meters. So that by that conversion, we can get this is equals to 2L. Means rho is 20. If we substitute, for example, if I multiply this thing to SI unit system, 20 100 centimeter over 1 meter times, then 1 kg over 1,000 gram. Then we can get 2 kilogram per meter. This is 2 kilogram per meter. Okay, so rho L is equal to 2L in SI unit system. This is in kilogram now. So once we get this M, total M is equals to MT is equals to 4 plus 2L. So what we are going to find is L, so that let's put it in this form. Now the natural frequency of this system, omega n is equals to Q over MT. So K is already known, 1,000. K is 1,000. 1,000 over MT is 4 plus 2L. Okay. Now we have a condition known as resonance. That means omega n is equals to omega. So at resonance, we have omega is equals to omega n. This implies that 15 is equals to these parameters. Radical of 1,000 over 1,000 over 4 plus 2L. Okay. Now equating this and this, we can get L is equals to, yeah, if we square this, we can get 225 is equals to 1000 over 4 plus 2L. From this, L is equals to, we can find the L value, which is equals to 0.22 meter. 2 meter, or it can be 22 centimeter. Yeah. So L is equals to 22 centimeter is answer for this question. Yeah. Another question number 3. 2 kilogram block of orange juice contains the instructions shake well, and an engineering student decides to get smart and connect the juice box with spring, which has spring constant 25 Newton per meter, and applies a Faraday force. The Faraday force is described F is equal to 5 sine 5t. 5 sine 5t. This is not visible. Here it is 5t. What is the maximum amplitude of the periodic motion and magnification factor at steady state? So two things are there: the maximum amplitude of motion and magnification factor are the two requirements here. So this is the given. There is a block having some exciting force of T. K is here. So let's take the free body diagram. F of K, the force of the spring will be in this direction. This is the exciting force. There is a normal force, which is from the base. So we consider frictionless surface. So the normal component is not under consideration. Okay. Here it is assumed frictionless surface. So F minus Fk is equal to m times mass times acceleration in the x direction, because it is accelerating in this direction. So F is known, it is 5 sine 5t minus kx is equal to mx dot dot. So from this we can get the governing equation. In this, the maximum amplitude F naught, F is equal to F naught sine omega t. So we can see this is F naught. And another quantity which we can find here is 5t means this is omega t. Actually, we call F of t, the forcing function F of t is equals to F naught sine omega t. So our omega is also 5. This is 5. F naught also is equals to 5 Newton and 5 rad per second. So we can get those information from here. And omega n is equal to k over m. So k is already given 25 Newton per meter. Okay, m is 2 kg. Yeah, it is given. So we can get 25 over 2 and the radical, that is omega n. Now the amplitude of vibration x particular is equals to F naught over k, or the steady state amplitude x is equal to F naught over k over 1 minus omega over omega n. Omega is the forcing frequency, omega n is the natural frequency. The whole square sine omega naught t. Omega naught is the forcing frequency, that is 5 here. So x max is equal to this component. We leave this trigonometric part so that 5 Newton over 25 Newton per meter, that is K over 1 minus 5 over under radical 25 over 3. So this gives us 0.2 meter X max, that is maximum amplitude of vibration equals to 0.2 meter. And the magnification factor, which is equals to X particular or the steady state amplitude over static deflection of the system, which is equals to 1 over 1 minus omega naught over omega n square, which gives us -1. So magnification factor is equal to -1. So this is a solution for question number 3. And the solution for question number 4 is actually the question we can see here, small ferry wheel with mass 20 kilogram is mounted on the end of horizontal beam. This is our horizontal beam for no apparent reason actually. The wheel is mounted centrically in such a way that, okay, the centric is equivalent to mass of 5 kg, located 0.15 meter away from the axis of rotation. This is the axis of rotation here, and the centric mass are placed in 0.1 meter away from the axis of rotation. The static weight of the ferris wheel causes a deflection of, so static deflection 20 millimeter is given. Given that the wheel spins at rate of omega and the forcing frequency omega is equals to 15 rad per second, find the steady state amplitude of vibration. So it asks us, we are requested to find the static deflection, no, steady state amplitude of the mass. So similar to the first question, we can find the free body diagram. You see, these are the eccentric masses which are rotating like this. So this eccentric mass produces force, excitation force. Okay, so that F naught is equal to mr omega square, or mass times centrifugal acceleration. So that centrifugal acceleration omega square r. Okay, so that gives us F naught. F naught is equal to 168.8 Newton. And this this force produces, actually there is a static deflection, deflection of this beam initially due to the static weight. So it is already given, okay, 20 millimeter. Okay, so let's go. Now, modeling this beam as a spring material with mass m, the mass of this thing, the combined mass acts on the beam, so the beam will deflect, and the beam itself is elastic beam. Okay. Elastic beam with some k value. So F is equal to kx, and which is equivalent with mg in the static deflection condition. F is equal to kx, which is equal to mg. Kx is equal to mg. Kx is equals to mg. From that, we directly find the k. K is equal to 9810 is obtained from this formula. Okay, mg over x, or this x is most of the time we call it as delta. This is delta rather than more x. We can express it as delta. Okay, once we get the k value, the steady state amplitude x particular, which is equals to F naught over k over 1 minus omega naught omega n the whole square. So the coefficient of this equation is, this is steady state solution actually. steady state solution, but the coefficient indicates the maximum amplitude. So x steady state amplitude x max is equals to f naught over k over 1 minus omega naught omega n square square. From that we can find 0.0318 meter is the x. Okay. So omega n is equals to k over m. So we can find omega 22.147 rad per second because weight is 20 kilogram. Okay. Weight 20 kilogram is there. Stiffness is calculated like this. Then this is the natural frequency, and this is the amplitude. So these are the questions. So maybe it is helpful for you. Some can use it. This is all for today. Thank you for watching.